Good afternoon, everyone, and welcome to today's webinar, COVID-19 UVC Devices and Methods for Surface Disinfection. I want to make everyone aware that we may experience some technical difficulties due to so many people being on the network. In addition, this webinar is recorded. For webinar support, please send an email to caesarcoms@epa.gov. Next slide, please. Your audio is muted, so to ask a question, select Q&A on the right side of the screen and type your question in the box, then select Send. Feel free to type your question in the Q&A box at any point during the webinar. We will also have a Q&A session at the end of the webinar. Closed captioning is available. Select Captions/Subtitles in your video controls. To change the caption language, select Settings, then Captions/Subtitles, and choose a language. Next slide, please. Anyone on today's webinar may receive a certificate of attendance. To do so, you must attend this live webinar for 60 minutes. If you did not request a certificate of attendance upon registration and would like one, send an email to caesarcoms@epa.gov. Just a note, EPA cannot guarantee the acceptance of certificates by your organization, nor can certificates be provided for viewing the webinar recording. Next slide, please. Thank you for being with us today, and now it's my pleasure to introduce our presenters. Dr. Lucas Odiant, Research Physical Scientist with the Office of Research and Development's Center for Environmental Solutions and Emergency Response. He's currently leading research efforts to assess alternative disinfection technologies like UV light, ozone, and steam to clean surfaces contaminated with SARS-CoV-2 virus. Next slide, please. Dr. Catherine Ratliff, Research Physical Scientist, also with the Office of Research and Development, whose current research focuses on understanding and quantifying how contaminants move around in the environment, as well as predicting the efficacy of different decontamination and disinfectant practices in complex settings. With that, I will turn it over to our first presenter, Dr. Lucas.
Can you hear me?
Yes, I can. Thank you.
Great. Thank you. Thanks everybody for joining Dr. Ratliff and myself for this webinar. Today we're presenting research that we have conducted in the last couple of months in relation to the disinfection of surfaces contaminated with the SARS-CoV-2 virus with UVC light. The outline of the presentation will be that we'll be talking about some of the background and the objectives of this study. We'll try to define, for those who are not familiar with the concept of ultraviolet light, what we mean by UV light and UVC light specifically. We'll identify some of the light sources that we have used so far in our research, the viruses that we are studying. We are investigating SARS-CoV-2, but also potential surrogate viruses. And then we'll talk about the data that we have collected for the MS2 virus as a surrogate, as well as SARS-CoV-2 in relation to UVC disinfection. We'll conclude this presentation with the conclusions and some practical applications and challenges that we have identified and the next steps that are to be done for the research. So a little bit of a background. Clearly everybody is familiar with the current pandemic, the COVID-19 pandemic, and the interest especially in cleaning services. There are already a large number of products on the market that can be used for the service disinfection. We are focusing here more in products that work in a maybe in a public transportation agency environment or in a large office area. A couple of things to point out is that they are widely marketed. A lot of people are seeing them maybe on your personal Facebook page, that there are UVC products coming to the market. EPA does not register pesticide devices. EPA only registers pesticide products. And this is an example of a pesticide device. That does not mean, of course, that false claims can be made. That's just to keep that in mind. So the project objective was to assess a couple of approaches for disinfecting challenges of materials, for especially when they were applicable to porous materials, and see how they would work when they were applied in a more complex environment. Think of a subway car or maybe a office space. We made an initial selection of 3 different approaches. One was based on UVC light. The second one is to look at ozone, and the third one is to look at steam. We identified upfront kind of in disinfection performance goal. That was a 3-log reduction, which is equivalent to a 99.9% reduction in viable infective virus post treatment of the specific decontaminants of choice, UVC, in this presentation. It should be recognized that that is not a hard number. People or entities that may think about UVC may have different goals in mind. This was surely a approach for our research effort. So a little bit about the UVC terminology that we're using. Everybody has probably seen a spectrum in the past that ranges from the very short wavelength in gamma rays, X-rays, ultraviolet, into the visible, into microwaves and radio waves. Within that is this ultraviolet area, and that has distinct 4 features that are identified. We're focusing in here on this what is called shortwave UV or ultraviolet C UVC. That is the area we're interested in, and why we're interested in it is actually on the right side. You see a typical example of a action spectrum of how efficient it is to inactivate a virus. The example that is shown here is for MS2, a bacteriophage. The actual action item for spectrum for the SARS-CoV-2 is unknown as of this month, but it gives you an idea that possible inactivation can happen at a maximum near 260, 270 nanometers, and may actually also go up to the lower wavelength range at the lower end of the UVC. We should point out that all the UVC research that we are talking about here is expected to be used in the absence of people when the lights are on. UV by itself is classified as human carcinogens by DHHS as well as the World Health Organization. So any of these devices as implemented as we're talking about here would not be turned on when people are present in such a environment. So when we started this research now about 6 months ago, very limited or no data existed related to UVC disinfection against the SARS-CoV-2 virus itself. Since then, clearly some laboratory studies have been conducted and are slowly coming to the publication status. And some of that information actually includes some of the dose response data that is relevant for the research and the implementation of UVC light. However, a lot of those studies are limited in scope and may only look at one material, may only look at one type of inoculum, and may not have actually may not use realistic exposure conditions that can be used for an activation of a virus in a much larger area like a metro car or a office space. Last point to point out is that whatever was published so far in relation to SARS-CoV-2 or previous viruses, coronaviruses, or surrogates of other viruses, is that there is a large variability in the efficacies that were mentioned due to the variation in the test conditions. So we identified 3 light sources. The first 2 light sources were identified through collaboration with stakeholders like Los Angeles Metro. They were interested in implementing UVC technology into their metro cars. We recognized that New York City had the same kind of interest as well. You saw on one of the first slides actually a picture of that, of a demo that we used actually the pulse xenon light source that we tested in our facility as well. So the 2 products that we tested mostly are a pulse xenon light source from Pure Lighting and Violet Defense. We should recognize that there are other vendors on the market that sell different similar type of products that also are based on the pulse xenon light. What they are expected to do is essentially that they should always complement normal regular cleaning. They're never intended to be the one approach that does everything. It is always in addition to regular cleaning. The intent for this specific light source that it would be brought in, say, into a metro car for maybe 30 minutes exposure and then taken out, and that would then hopefully do a good job in disinfecting surfaces. So that's kind of more a roll-in, roll-out approach. The middle one is a light emitting diode. We received one from the Transport Design Group, TGG, who is working with Helios on this specific light emitting diode. We should recognize there are a lot of other vendors on the market that now produce LEDs also in relation to disinfection for SARS-CoV-2. They are more intent maybe to be built into a metro car or into an office, so they will be turned on when people are not present overnight and can potentially be turned on for a longer exposure time of 4 to 8 hours. The last one that we wanted to bring up is that you also have the traditional mercury lamps. We used one that we had in a biosafety cabinet. It's a low pressure mercury light. It's widely used for the purpose of cleaning of surfaces, and usually take long exposure hours to get that. The reason why these are probably not heavily marketed as a commercial product for consumer use is the fact that they contain mercury and have therefore a kind of a health concern with it as well. So what are the differences? And that's where you see that things are a little bit more difficult than just say UV is UV. For the xenon light, the wavelength spectrum that it emits is different from a light emitting diode and different from a mercury light. And that's illustrated in the graph here on the right side, where you see the wavelength on the horizontal axis and the intensity normalized to an equal irradiance in the UVC range on the vertical axis. And what you see is that for the pulse xenon light, you have a very broad wavelength spectrum that extends well into the UVB and the UVA and even into the visible. While the LED, in the case of the project that we're using here, emits actually two wavelengths, one at 270 nanometers and one at 400 nanometers. There are two light emitting diodes in that unit included. So both are present in the specific experiments. The last one to point out is the mercury light that has a single wavelength of 254 nanometers and emits that continuously. One point to repeat, and I forgot to mention that actually, is that the xenon light is a pulsed system and delivers all the energy that it has in one bright pulse on the length of a couple of milliseconds, and that pulse is repeated once every 6 seconds. So two things to keep in mind when we talk about light measurements. One of the things that we will be talking about dose. And by dose, we always mean the intensity of the light reaching the surface multiplied by the exposure time. Dose is kind of the variable that you are interested in determining when you start looking at how efficacious is a specific technology, how good is it working, or what is it doing, and dose is the main parameter in that. The other thing to point out is this, that the dose is related to the intensity, and more specifically, it's related in inverse square relation. So the further you're away from the light source, the lower your intensity or your dose will be at this same contact time. So keep that in mind. For something that may be working very well at 5 inches distance and may claim a high efficacy there, will probably not work at 100 times or at 10 times 50 inches distance, because then you're 10 times the distance or factor 100 lower in an actual dose that it is receiving. Two types of light measurements can be considered. We looked at the dosimeter meter paper, as well as more frequently used UVC light measurements. We relied on a specific detector that we alluded to here, which is a sensitivity in the UVC range 220 to 280 nanometers. What are the target viruses we have used so far? First of all, we had two potential surrogate viruses, MS2, a bacteriophage, and 5.6, as well as the SARS-CoV-2 virus. The reason why we actually worked with the surrogate viruses is that a lot of the research that we tried to do with SARS-CoV-2 would be very expensive. And therefore, we had to reduce that research effort with SARS-CoV-2 to the limited number of tests and do more of the material sensitivity of the results, as well as changes in how the inoculum changes the efficacy with the surrogate viruses. So for those who are not familiar with what these viruses are, this is a graph that was put together by Dr. Worth Kelvey, and I appreciate him sharing it with us. Is that the MS2 is a bacteriophage that is a non-enveloped virus, which is a little bit different from the other ones like the 5/6 and especially the SARS-CoV-2, which is an enveloped virus. It is expected in a general order that an enveloped virus like the MS2 would be least resistant to any kind of inactivation, and the enveloped viruses that are actually at the bottom should be the easiest to inactivate. That's at least the general consensus. So the test matrix that we were working with differs a little bit between whether we were using the SARS-CoV-2 virus or the MS2 and 5/6 surrogate viruses. First of all, the light source that we tested it on were essentially the same. We have additional data, you will see that later, with related to the mercury lamp for the MS2 and the 5/6. The materials were slightly different. We had the stainless steel on both sides, maybe a different grade or different type. We had other materials included, glass, stainless steel, and ABS plastic, which are commonly encountered materials in a subway car. That was what they were included. We also included a bus seat fabric. Needless to say, it's found in your bus seats in a metro, in a large sorry, I lost my train of thought here. Apologizes. So it is found in buses in a lot of places. We also look at what's the type of inoculum we were applying, whether we had multiple droplets applied or whether it was a single droplet. There's also a difference in the matrix that we were testing it in on the MS2 and 5/6. We focused on one standard approach, that is a standard approach of a PBS solution. Well, for the SARS-CoV-2, we actually looked at the tissue culture media as well as the simulated saliva based on the ASTM method. We also looked at whether the inoculum was present as a wet droplet or as a dry droplet. And by that we mean that when we talk about a dry droplet, means that the droplet was dried prior to the application of the UVC light before we started the actual inactivation. Last thing to point out was that we have limited data on the SARS-CoV-2 that you will see later on in the presentation. We have a significant number of tests completed for the MS2 and 5/6. Last slide on my side before I hand it over to Dr. Ratliff is this alludes a little bit on how we inoculated the coupons. We would apply, in this case for the MS2 and 5/6, a small number of droplets and then essentially spread it out over the surface. That was most of the common application method. For the SARS-CoV-2 materials, we actually used five droplets that was applied twice, so you get 10 microliter droplets 10 times applied to the surface. They were not spread onto the surface further. Experimental setup is relatively straightforward. On the left side shows the layout of the coupons. The light itself is not visible, but it comes in from above. And the materials you will see identified are your seat fabric, your ABS plastic, and the stainless steel coupons that are laid out. On the right side, you see the setup as it was done for the MS2 and 5/6 research. We had a pure light source on a stand, and we would expose the coupons to this light, either with the coupons in a vertical orientation or in a horizontal orientation. And the meter in between that you see is our power and energy detector. Last thing to point out is how did we recover the viruses. Without going into the extreme details on this, it comes to the point that we would expose the coupon to the UVC light, at least the test coupons, and then we would extract them by placing them into conical tubes. They were vortexed. and then using common microbiology or virology technology approaches were diluted and series were prepared in various plaque assays according to the specific virus or bacteriophage that we are looking at. After overnight incubation, PFUs were enumerated, and that gives you the results for the MS2 and the 5.6. For the SARS-CoV-2, the samples were actually split. We are also looking at analysis by RT-PCR. We will not be reporting on that. That is still in progress. We do report the results as measured by TCID50, the median tissue culture infectious dose. What you will see on the next couple of slides a lot of times is the term of log reduction. And by that we mean is the reduction in the recovery from of the virus from the positive controls minus that of the what was recovered from the test coupons. And positive controls are the ones that are not exposed to UVC light. The test coupons are the coupons that were exposed to UVC light. With that, I'm turning it over to Dr. Ratliff, who will be talking about the first set of experiments.
All right, thank you, Dr. Odions. And before diving into the actual lab results, we want to touch first on some results that we got from a field study. Next slide, please. So as Dr. Odions mentioned, we've been collaborating closely with LA Metro throughout the pandemic, looking at evaluating different types of disinfection technologies that could be implemented in different subway cars or buses. And LA Metro is particularly interested in using the pulse xenon light that Lucas has touched on earlier today, and in particular they were interested in evaluating some practical considerations in using these lights as part of routine disinfection practices, such as how easy it was to bring the lights on and off of a subway car, as well as how the electrical load was impacted, how the lights held up from a durability standpoint, and so on. And so we collaborated with them to provide some MS2 inoculated small coupons. So they were shipped from our lab in Research Triangle Park, North Carolina, all the way to LA. And they included those MS2 coupons in their test to evaluate not only some of the practical considerations, but as well to take a look at how effective the lights were against MS2. And in addition to putting the MS2 in different locations throughout the rail car that LA Metro deemed of interest, they measured the UV dose at each of these coupon locations for different test setups. So in particular, LA was interested in looking at 2 different light configurations and wondering if by doubling the lights, they were able to achieve twice the dose at these different locations, which would then hypothetically allow them to cut back on the amount of time that the lights were deployed in the car, which would help to speed up the process of moving these lights in and out of the cars. So down on the bottom right is a little chart with the different light configurations and the different test or the different exposure durations that LA Metro was considering in this field test. And something to note too for the next few slides when we talk about UV dose here, LA Metro's detector, UV detector, picks up not only UVC but also UVB and UVA. So we'll be talking about dose with respect to their detector for the next few slides. Next slide, Lucas. So here is a picture or a figure of their experimental setup. So this is one of their rail cars with the rectangles here representing the light locations and the blue circles representing the locations where the coupons were placed, and again where the dose measurements were taken throughout this field test. So again, they, in addition to having the coupon out where the dose was measured for each test condition, those data are recorded for each of these figures. It's a little hard to see, but each bar represents a different test where all the orange bars were collected on one day and all the green bars were connected on the next. And it's not important to see the details here, but generally speaking, something that was reassuring from this is that the dose at each of these locations for each of the test configurations was generally about the same from each set of experiments, so day-to-day repeatability. Next slide. And this range of doses that was measured within the field test for the different configurations of lights range from about 1 to 22 millijoules per centimeter squared. Again, knowing that this was not just UVC, but extended farther with the broad wavelength pulse xenon light and the detector that picked up these broader wavelengths as well. And it's no big surprise that they saw the lowest doses at the locations that were either outside of the direct line of sight or at larger distances away from the light. And the highest doses were achieved when the detector or the coupon were positioned really, within direct line of sight of the light and for the longer exposure time. So the highest dose was at about 60 inches away from the light and for about 30 minutes of exposure time. And as I mentioned before, there was a high reproducibility in doses, generally speaking, from day to day. But something that was interesting to us and left us a little perplexed at the time was that we really didn't see any significant reduction in the MS2 coupons that were exposed to the UVC light relative to the control coupons that accompanied those test coupons. So again, like I mentioned, we were a little surprised by this, and we decided that we needed to get in the lab and conduct some additional tests to understand this lack of inactivation of MS2. Next slide. So now we're going to talk a little bit about our MS2 and Phi-6 research. Thank you. Next slide. So in addition to focusing in on that range of doses that LA Metro saw in their field tests, we wanted to expand to looking at a wider range of UVC doses. So here's an initial plot of some of our initial MS2 and Phi-6 results. So the MS2 dots are in blue, and the Phi-6 dots represent the results in orange, with the UVC dose here on the x-axis going back to that more UVC limited detector. So again, for the purposes of the rest of the talk or the webinar, we'll be talking about UVC dose limited to that detector optimized to look at just the UVC portion of the wavelengths. So here, as I mentioned, UVC dose is on the x-axis, the log reduction is on the y-axis. So it was a little bit, again, surprising that even at significantly higher UVC doses, we still weren't seeing the 3 log inactivation that was our disinfection target for the purposes of this study. So at low doses, the dose response looks somewhat linear, but up at higher doses, we see this plateauing of our results. And we didn't see initially that we were able to achieve that 3 log inactivation. So again, there appeared to be this nonlinear relationship for our initial experiments conducted on stainless steel. And for reference, here that dashed line way close to the, pretty far over to the left on the x-axis is the highest dose that was measured as part of the LA Metro field study. So after doing these initial experiments in the lab, we realized there was actually agreement between what we were seeing in the lab and what we were seeing with LA Metro, and that the relatively low doses that were achieved in the railcar weren't leading to a lot of inactivation of MS2 in the lab either. Next slide. So we started to look at different types of lights, thinking that maybe different lights would have a different dose response curve. So those initial results we showed you in the slide before are here on the left. And we looked also, as we mentioned previously, at a low pressure mercury lamp. So those are the results on the top right, and also with an LED light, and those are the green dots down on the bottom right. So all of these results are for MS2. So you can see that the same nonlinear behavior appears for each of these 3 UVC sources. Next slide. So then we thought, well, maybe there's an impact with the material and how the virus is sitting on the material. Maybe that has some control over how effective UVC is with these in inactivating these viruses. So in these 2 figures, the pulse xenon light results are on the left, the LED results are on the right, and the filled in circles are with the MS2 on stainless steel, but the open circles are with MS2 inoculated on glass. And so while we see the same somewhat nonlinear relationship between the dose and the log reduction, generally speaking, the inactivation of MS2 on glass tended to be much higher than on stainless steel. So you can see here for both the pulse xenon and the LED lights, we were able to achieve greater than a 3 log reduction. Next slide. So that left us again scratching our heads a little bit. The stainless steel to the eye looks pretty darn smooth, so does the glass. But we actually took some pictures or some images on a scanning electron microscope, which allowed us to get really, really high resolution images of these surfaces. And that was really insightful. So on the left is an incredibly zoomed in image of the 304 milled stainless steel that we have used for our MS2 and Phi-6 lab work. And on the right is a really zoomed in picture of the glass surface that we used for the MS2 and Phi-6 study. So you can see that on the left, even though to the naked eye, stainless steel looks really smooth, there's a lot of crevices for the stainless steel that we were using that could have been potentially shielding or shadowing some of the MS2 and preventing the light from actually being able to inactivate it. And the image in the middle is a picture of the 301 stainless steel that was used in the SARS-CoV-2 research that we'll touch on a little bit later. So it's somewhat in between the milled stainless steel and the glass. Next slide, please. So we also investigated the impact of the inoculum condition at the start of the experiments. We looked at whether the droplets were wet versus dry and whether the inoculum was spread out versus left as a droplet. And essentially, we saw that generally speaking, wet inoculum or wet droplets tended to be easier to inactivate or lead to a higher efficacy than dry droplets. However, we didn't see any significant trends in terms of the spreading versus the droplets making an impact in efficacy, so that there may be some slight differences in terms of spreading versus leaving the inoculum in a droplet depending on the material, but there's no clear trend there. Next slide, please. So in summary, and just to point out, these two figures on the left summarize both the MS2 inactivation by the pulsed xenon light on the top and the Phi-6 inactivation by the same light on the bottom. But here I want to note that the X scale is in a log scale. So we do for both MS2 and Phi-6, and on two different types of materials, we see this nonlinear dose response behavior, which is really important to keep in mind, because something that is really, again, important to consider is that if we think about the amount of UVC energy or the dose required to inactivate 1 log or 90% of a virus, we can't just simply think about, okay, if we need 3 times the energy to get 3 times the dose response, that there's a nonlinear relationship. So we can't use that 1 log efficacy dose to extrapolate linearly to a 99.9% or 3 log disinfection dose. So that's, again, something really important to keep in mind here. And we also found that generally speaking, the log reductions were higher for wet inoculum versus dry inoculum, and there's no real impact on spreading versus droplets, no clear trends there. And again, generally speaking, the log reductions for glass, especially at higher doses, were noticeably higher than for stainless steel, and that's for both of the light sources that we tested that with. I think next slide, please, and we'll hand that back over to Dr. Odions.
Great. Thank you, Dr. Ratliff. Do you hear me?
Yes, I can hear you.
Great, thank you. All right, so before we started our research with SARS-CoV-2, we wanted to make sure that we were doing that under the right conditions. So we went through extensive method development, and that consisted of, for example, demonstrating that we could actually extract the SARS-CoV-2 virus from these materials, the ABS plastic, the stainless steel coupons, and the STEET material. We were able indeed to do that, and we're able to recover more than 10 to the 4th PFUs per coupon. So that was a good start. That also included, actually, after initial drying of 1 hour of the inoculum onto the surface, which by itself creates a loss in viable viruses. Anyway, the other thing to point out was that we did not find any cytotoxicity of the materials. We fortunately didn't have to go through a more rigorous assessment whether any kind of decontaminant is present that may actually bias the results, because UVC is not a part of that. We clearly were also able to identify what our detection limit was for the TCID50 analytical method, and in this case it was 6.3 virons per coupon. So this is a graph of first results of one of the test conditions, and instead of jumping straight to the log reductions, I wanted to illustrate it with the recoveries that were obtained from various materials, both positive controls and the test coupons. So in this graph on the left, you see groups of 3 materials: bus seat fabric, ABS plastic, and stainless steel, and it repeats itself 4 times. Because there were different conditions were tested. We had the SARS-CoV-2 present in tissue culture media, but we also had it present in the simulated saliva. So that splits up these 2 groups here. Then there's also a distinction between whether the UVC inactivation started with the droplet present as a wet droplet or as a dry droplet. And that are makes you that you see these graphs showing here. On the vertical axis is clearly the log recovered of viable viruses, and the blue graphs are the positive bars are the positive controls, while the red bars represent the test coupons. So that's kind of what we see here. We see that we have better than 3 logs in recovery on all the positive controls in the tissue culture media. We do not see it as high in the simulated saliva, but we are still above the 3 log reduction, so that we are at or very close to the capability to demonstrate the potential 3 log reduction if that is applicable to the specific UVC disinfection approach. That's kind of what this graph shows, and you can take this information and just essentially take the difference between the blue and the red bars and determine from that what the log reductions are. So how does it look like? That is on the graph here. Here again we have now 2 groups of data. We have the repeated the bus seat fabric, the ABS plastic, and the stainless steel when the SARS-CoV-2 virus was in the tissue culture media, and on the right side is a set when it was in the simulated saliva. And there is a difference in the log reduction that we found clearly. Bus seat fabric is very difficult to handle by saying that the inactivation of the SARS-CoV-2 is very difficult. It's less than 1 log in reduction for the specific test condition. On the opposite is that for the ABS plastic, we do see a better than 3 log reduction, especially when we are starting with a wet inoculum. When it is a dry inoculum, you do see a drop off, but we are still above 3 log reduction for the tissue cultured media. Now, the story is a little bit different when we are talking about simulated saliva, which is indeed more realistic to what we see in the field, or what would be encountered when you start cleaning a surface in a metro car or in an office space. There the log reductions are significantly lower. We do see one occasion where we have non-detect, so this is essentially the highest you could get. So technically speaking, this could have been a better than 3 log reduction, but we just did not have quite the amount of number of viruses on the surface to demonstrate that. The most challenging one is a dry inoculum in a simulated saliva environment, and that is fortunate because that is the most realistic scenario you may see in a field setting. So we did these tests 3 times for 3 different doses, and on the left side you see a summary of those results, and instead of plotting everything in one graph, it is split up in 4 types of conditions, ranging from either working in the tissue culture media with wet droplets in the top left, the tissue culture media and the dry droplets in the bottom left, then for the simulated saliva and the wet droplets at the start of the UVC disinfection on the top right, and the simulated saliva with the dry droplets are on the bottom right. And the log reductions now showing us a dose response curve in this graph here. Not too surprising based on what you saw on the previous slide. The highest log reductions can be found for the SARS-CoV-2 virus present in the tissue culture media. We get better than 3 log reductions for most of the conditions that we have tested. We tested actually 3 test conditions. One in the middle one is the one you saw on the previous graph. We went to essentially double the dose and did not see much of an improvement at all for most of the other conditions that are shown here. When you go to half the dose, you do see a drop-off in log reduction, but it again shows this nonlinear behavior that Dr. Ratliff alluded to for the MS2 and 5/6 as well. You cannot just predict upfront what it is going to look like based on a presumed linear relation between log reduction and the dose that you are exposing the material to. Last thing to point out is the actual exposure times that were used for the specific light source to get to this dose are indicated here, and they range from the 7.5 minutes for the lowest dose through the 30 up to the 60 minutes. So what we clearly see is that there is a significant drop-off in log reduction for the simulated salivas. And we believe that that is definitely related to the fact that the UV light gets absorbed in the saliva. Saliva contains protein, contains salt. They all attribute to an absorption of the UVC light itself, and therefore impacts the degree in which it is able to disinfect the virus itself. The last thing to point out is that the LA Metro highest UVC dose that was measured in the test, in the field study, is actually in the range of this 3.5 millijoules per square centimeter. So it does not really bode well to see a very high efficiency under the conditions that they were measuring it with the specific light source. So we did a comparison also with our other UVC light source, the light emitting diode. So the log reductions that you see in the graphs here are on the left side for the pure light source at a 30 inches distance, but a 60-minute exposure time, versus a light emitting diode that was only emitting light at one specific wavelength. And it was also kept at a 30-inch distance and a 60-minute exposure. So you can compare them in a way side by side, as being that they were just exposing their light to the same surfaces under the same distance and same dose conditions. And what we see is essentially that they are behaving very similarly. There might be minor differences there, but they are not very dramatically different. So to that extent, the pure light source that we tested here seems to be behaving in a similar manner as the light emitting diode that we got from TJG. Last thing to point out is that we are still working on additional collecting data for the light emitting diode. So more results are pending on that topic. This gives us also the opportunity now to compare our results from the MS2 and to a less extent the 5.6, which we're still working on, with the SARS-CoV-2 data. And what is shown here is essentially an accumulation of the SARS-CoV-2 data for the three materials, the bus seat fabric, ABS plastic, and stainless steel, and the MS2 the materials for stainless steel and glass. The blue shaded area are essentially most of the log reductions that we found for the MS2, while the similar log reductions at specific doses were found for the SARS-CoV-2 are in the green shaded area. And generally speaking, we see that indeed MS2 is a little bit more difficult to inactivate, which makes it therefore a more suitable, or makes it a suitable surrogate for this type of research with UVC lights. We should still point out that there are still small differences between these two data sets. The stainless steel surfaces are not exactly identical. Similar to that, the inoculum deposition is a little bit different, as well as the composition of the inoculum itself. Research related to or in relation to the 5.6 data is still in process. We didn't want to present that here in comparison here. So this is kind of a good indication that MS2 is a suitable virus for SARS-CoV-2 research by UVC disinfection. With that, I'm going to hand it to Dr. Ratliff to wrap it up with the conclusions.
Great, thanks, Dr. Oudjians. Can you hear me okay?
Yes, I can hear you.
Great, thanks. So just some conclusions to wrap up our webinar. We did find that the UVC light that we tested, the various different sources, did inactivate SARS-CoV-2 and the bacteriophages MS2 and 5.6. We found that the efficacy of these various lights depended on the material or the substrate that the virus was on for the testing, as well as the composition of the inoculum. And we also found that the condition of the inoculum, so whether it was wet versus dry or applied in droplets versus spreading, could also impact the efficacy of the UVC light. We also found that microscopic features of what appear to be smooth surfaces can cause microshadowing that may lead to some shielding and therefore lower the efficacy of UVC in inactivating these viruses. We also found that MS2 appears to be a pretty good surrogate for SARS-CoV-2 with UVC testing because it is slightly more difficult to inactivate. And generally speaking, we found that there's a large number of variables that can impact these various UVC studies, and it makes it really challenging to compare our results or even other published results side by side because there are so many different factors and moving pieces in conducting this research. So we think that a standardized method for evaluating UVC disinfection would really help to compare different UVC light emitting devices and compare more apples to apples and fewer apples and oranges. Next slide, please. And also we wanted to summarize a few different practical considerations in our evaluation thus far, and the research results point to some of these challenges. So here in the conditions that we tested, we saw that the UVC dose needed to achieve the 99.9% or 3 log inactivation of SARS-CoV-2 spanned across a fairly large range, so from about 6 millijoules per centimeter squared to greater than 22 millijoules per centimeter squared, depending on multiple variables. And again, that dose is as measured by our specific UVC 270C detector. We saw that for the operational conditions, or the timing that these lights were intended to be used in the field or in rail cars or in office buildings, so generally speaking, they're intended to be deployed for, say, less than an hour. If those are the durations for exposure, we found that the UVC dose that is necessary to achieve any sort of effective inactivation can only be achieved at relatively short distances, so say about 30 inches or shorter. However, efficacy could be improved for longer exposure times, and I say can be improved because that's slanted towards the left side of those dose response curves, where there's some impact or some improvement in the efficacy with higher doses. But if you can recall that because of that nonlinear response, we do see a plateauing of the efficacy after a certain period or after a certain dose has been achieved. And another way that we could potentially see improvements with UVC lights implemented for disinfection practices would be the addition of multiple lights that may cause or reduce the amount of shadowing or even micro shadowing on surfaces if lights are coming in from different angles. And so another thing that's really important to keep in mind is that UVC light is only going to be effective where the light can actually impact the viruses on the material. So there has to be a direct line of sight between the light source and where the contamination is. We also saw that porous materials, or especially materials like the bus seat fabric or carpet that have a lot of texture will tend to shield the virus from light. And so the disinfection on those particular surfaces will be less effective with UVC light. Next slide, please. So as Dr. Odions mentioned, this is ongoing research. This is a work in progress update. We are continuing to evaluate UVC to address the impact of these various different variables, and we will be comparing our results to the slow trickle, I shouldn't say slow trickle, there's more research coming out from other labs and groups about the effectiveness of different types of UVC against SARS-CoV-2. We also are continuing, in addition to the UVC work, we're going to be switching our focus to evaluating the effectiveness of ozone and steam against SARS-CoV-2. And in addition to the efficacy research, we have some other UVC related research that addresses some of the practical considerations of implementing UVC as part of routine disinfection practices, including better characterization of these light sources, as well as understanding and characterizing the reflectivity of different types of materials. And we also are planning some material compatibility tests. Next slide. So we'd like to touch briefly on some acknowledgements. There's a large group of people that have contributed to this work, and we're very grateful for everybody's assistance. Our biolab staff in our Research Triangle Park lab has been integral in completing this work. Also, Jason Sante has been a key collaborator in helping us work with LA Metro, as well as participating in that field study. The staff at Battelle has been done a great job in conducting the SARS-CoV-2 research. And also we want to shout out a special thanks to LA Metro for being great collaborators on this work. And we'd also like to thank and acknowledge members of a large EPA project team that's provided support and feedback throughout this process. Next slide. So thanks again, everybody, for joining us today. Our contact information is up on the left. Another thing to point out on the right is a link to a research website where we're posting updates not only about this research, but about different types of research related to COVID-19, disinfection in the environment. There's also interim data reports posted on that website, so I would encourage you all to take a look at that. So with that, I think we're happy to take any questions.
Hey, Catherine, thank you. There's a lot of questions, so I'm going to try and go through as many as possible. One of the first questions is, what about shadows? Not all surface areas will receive the UVC radiation in a location because of shadows. Yep,
that is a great question and point. So essentially anywhere that the light is shadowed from, or whatever you're trying to inactivate is shadowed from the UVC light, that it won't be effective in those areas. So that's a great thing to keep in mind. There needs to be a direct line of sight between the UVC light and the contaminated surface.
And the next question is from a graph that was displayed in the presentation. It looks like 222 nanometers is more effective against SARS-CoV-2 than 265 nanometers. Is this correct?
Lucas, I'll let you take that one.
Yeah, the graph that we showed there was actually for the bacteriophage MS2. The exact curve is unknown for SARS-CoV-2 at this time, so that is still to be determined. If it follows the same profile, then the person who asked the question is indeed right that a lower wavelength may indeed be more efficacious or easier to inactivate the virus.
Okay, great. Thanks, Lucas. And the next one is, why was the fetal bovine serum added to the PBS? Was it 1 time or 10 times PBS?
It was 5% in the full amount. I'm not sure how it is in relation to the PBS itself.
But to add that the fetal bovine serum is added as a stabilizer, so it essentially it allows us to, or preserves the MS2 slightly, so, or the SARS-CoV-2 is used there, so it allows the stability of the virus to allow you to have essentially a higher dynamic range in evaluating the efficacy of the various technologies, because that essentially allows your positive control recoveries to be higher. But certainly if somebody has more specific information and wants to dig into that a little more, please reach out and we can answer some more specific questions.
Thanks, Catherine. The next one is, did you do anything to condition the output from the UV sources? Specifically, was there anything done to collimate the radiation before exposing the material surfaces to UV from these sources?
Lucas, you want to take that one?
Yeah, sure. No, the lights, the UV light that comes out of the source was impinging onto the surface without anything in between. The only caveat we want to make is that for the mercury lamp, we actually created a collimated approach to avoid that the full length of the mercury light would actually be impacting on the surface. But for the pulse xenon light, as well as for the light emitting diode, we did not add anything else. It is just the direct exposure of the UVC light to the surface material.
Thanks, Lucas. Which wavelengths did LA Metro test? Was it the 222 nanometers far UV?
No, the LA Metro test was done for the pulsed xenon light, and one of the graphs showed you that it actually emits UVC, UVB, and UVA and visible light.
And then this is always an important question. Is the 3 log reduction considered as disinfection?
To the best of my knowledge, and is that it is a definition of a disinfectant for viruses.
For the dose calculation of the xenon lamp, what wavelengths from the source spectra were included? Same question for the LED source.
That's a good point, and that points at a difficulty in the interpretation of the UV intensities. The pure light source emits a broad wavelength range, so multiple wavelengths, and each wavelength on its own may have its own inactivation ability of the virus. So as long as we do not have knowledge on the action spectrum of the virus, we cannot really say which part of the wavelength within that pure light that the pure light source emits is the most favorable one. For the LED light, that was 270 nanometers, and there was just a single wavelength assumed there.
Thanks, Lucas. And just to clarify, did you find in the LA field test that the UV treatment didn't deliver a strong enough dose to be effective, or did?
Catherine?
Sure, so that's correct. We found that there was no significant impact from the UV light with the MS2 in that particular field test. Something to note is that we did select MS2 to include in that test because it's a fairly hardy, as Lucas showed in the slide with the great table comparing the different viruses. It's a fairly hardy potential surrogate for MS2. It's non-enveloped. We chose MS2 for that particular study because we needed something that we'd be able to send from North Carolina all the way across the country to LA for them to use it in the field test and send it back and still have viruses recovered from that trip. So we knew that it was a potential, we know it's a potentially a hardier virus than SARS-CoV-2, but that is correct that we did not see any significant impact from MS2 in that particular study.
Thanks, Catherine. Have you performed any lab studies investigating the log reduction when dry droplets are then moisturized and treated with UVC?
We have not. That's a really interesting point. Part of our hypothesis and part of what's been put out there in the literature and other studies is that, as Lucas mentioned, those salts and various proteins, especially the salts when they crystallize in saliva, could be providing some actual shielding or absorption. So rehydrating the droplets would be something that is definitely interesting to consider, but not something we've thought about doing yet. Thanks for the question.
Yep.
And then we'll take a couple more. There's one, are there any plans to investigate the efficacy of 222 nanometers FAR UVC as produced by the Krypton chlorine excimer lamps for this application?
Lucas, I'll let you take that one.
I think we would like to. It's definitely an attractive alternative. We have not looked at it at this time, so that may be still something that we may consider in the future.
And I guess something maybe to note is that for those who are still listening in, that FAR UVC has been proposed as potentially a technology that could hypothetically be used while people are present. There are no long-term studies to understand the impact of, or to really evaluate with actual, human or mammalian data, the impact of that type of UVC on human skin or eyes. So essentially, because those studies haven't been conducted yet, that initially was not something we wanted to include in this study, but it is a potentially, an interesting option to keep in mind for the future as we get more data about the epidemiological impacts of FAR UVC.
Thanks, Catherine. Here's another one. Can you speak to the effectiveness of UVC disinfection used on airstreams? I've seen ceiling mounted UVC units that are intended to disinfect air as it circulates through a space. Can these devices effectively reduce SARS-CoV-2, and would this be safe to use while people are present in the space?
Catherine?
That's a great question. We have not evaluated the impact of UVC on aerosolized SARS-CoV-2 or MS2 or 5.6 yet. However, that is up and coming research that we do have planned to evaluate the potential for induct UVC. And so that technology is something that has been well studied. It is positive. UVC can be effective against aerosolized viruses and other type of pathogens or microorganisms. There are many factors that impact how effective UVC is on an airstream, including how quickly those viruses or other types of microorganisms are passing through the UVC. So you can imagine if you have a particular dose necessary to achieve a certain amount of inactivation, you need the airstream to be moving slowly enough through that UVC light to be able to achieve that dose for inactivation. So if the particles or the viruses are passing through so quickly they don't receive enough of that dose, then that induct UVC won't be as effective. We, like I mentioned, are planning to evaluate that with a particular induct UVC unit in upcoming research. So stay tuned. Keep a lookout on that COVID-19 and the environment research page we mentioned earlier, and hopefully in the next few months we'll have some results related to that particular technology.
Okay, we'll do one last question. Thank you. Subway cars are dirty places. Do you think the surface contamination would reduce the effectiveness of UVC disinfection methods given the reduction in efficacy saliva causes? Will this be looked at?
Lucas, you
Yeah, sure. I can take that. I think there is definitely a concern that the UVC will actually be that the cleanliness or the lack of cleanliness thereof of the surface may actually impact how efficacious UVC would be. That being said, it is intended UVC to be complementary to the standard cleaning procedures. So to that extent, it is probably the impact of a maybe slightly less or a dirty surface may not be as high because the surface should not be that dirty because they have already been cleaned before you would apply a UVC overall exposure. But it is recognized that very likely a dirty surface makes it more difficult.
Thanks, Lucas. It's 3 p.m., so that's it for our questions. I guess we can end the webinar, and here's contact information if anyone needs it.
Thanks, everybody.
Thank you.
For listening in.
Thank you.